Welcome to the first lecture for Chem 418, Nuclear Chemistry. This lecture is an overview of the course and how it is organized. In this lecture, we're just going to discuss the class organization, the outcomes of the course, and how the course will be graded. As one would imagine, radiochemistry is central to a range of topics within nuclear technology. A number of these topics are shown here. This course will emphasize radiopharmaceuticals and the work that is conducted in this area at the University of Washington. This will include a tour of the cyclotron facility at University of Washington where the medical isotope astatine-211 is produced. We will also discuss the nuclear fuel cycle, which includes separations of uranium as a source of nuclear fuel, the production of the nuclear fuel from that uranium, and the reactors that are involved in energy production. We'll also talk about radiochemical separations, waste forms that are resultant from radioactive isotopes and how they're disposed. We'll also explore nuclear forensics, which is identification of nuclear material, nuclear safeguards, which has to do with the prevention of the proliferation of nuclear weapons, and fundamental science associated with radioelements. An example of some of the fundamental and applied science relative to radiochemistry is shown here, where this structure of uranium and triethyl phosphate is shown. This is based on the separation of nuclear waste using the Purex process, which we will discuss later in the course. But it's an example of some speciation studies that can be performed using actinides, in this case the uranium, and is shown as the uranyl, as we'll discuss later in the course, where you see the uranium with these oxygens coordinated by the nitrate. And these phosphate groups allow the extraction into inorganic phase. One key aspect of this course is to increase the number of students with exposure and potential interest in radiochemistry. Ideally, this course will provide a route for research for students who have completed the course. There are research opportunities available in nuclear and radiochemistry at the University of Washington and also at U.S. national laboratories, one being in Eastern Washington, the Pacific Northwest National Laboratory. If anyone is interested in exploring these opportunities, I'd be happy to discuss them anytime during the course. The course includes the physics of radioactive decay and the chemistry of isotopes. Fundamentally, radiochemistry is at the intersection of the periodic table and the chart of the nuclides. The periodic table has structure, as chemists that one understands, that are based upon the electrons, whereas the chart of the nuclides has structures and describes properties that are based upon how the nucleons, the neutrons and protons, are engaged in the nucleus. So periodic table, electrons, chart of the nuclides, neutrons and protons within the nucleus. And within radiochemistry, we want to emphasize elements with only radioactive isotopes, since they're unusual examples. So as examples, technetium, element 43, sits in the middle of the periodic table. We'll discuss the chemistry of technetium, and we'll particularly focus on the chemistry of the actinide elements, which are those elements that have 5f electrons that are at the bottom of the periodic table. The course topics includes the chart of the nuclides, details on alpha decay, beta decay, gamma decay, and fission. You should understand what the differences are in those by the end of the course. Methods and data that are obtained from investigating nuclear properties. We'll have discussions on the fundamental chemical properties that are involved in radiation and radiochemistry, and particularly how they intersect with the elements that are only available in radioactive isotopes, such as technetium and particularly the actinides. We'll discuss how isotopes are produced, and we'll talk about how radiochemistry is used in research and technology. The textbooks that will be used in this course are primarily PDFs, and they'll all be linked to the Canvas website. The two textbooks that we'll use include Nuclear and Radiochemistry and Modern Nuclear Chemistry. And one thing that I want to note is that input from students are valued for this course. Participation is expected, and any sort of assistance with course development is valued. And the output obtained from the students should enhance the online course experience. The course has 7 outcomes where by the end of the course, the student should have some expertise, experience, knowledge in a few different topics related to radiochemistry. First outcome is understand, utilize, and apply the chart of the nuclides, table of the isotopes, to radiochemistry and nuclear technology. Primarily, this is understanding how to obtain the data that are presented in those documents and utilize that information. Another thing the students should understand is the structure of the nucleus. Often in chemistry, we ignore the nucleus, but within this course, we do want to investigate the fact that the nucleus has structure. Here, there's an example of an oblate, spherical, and prolate nuclei, and we will discuss within the course how this structure is understood and what's the relationship between the shape of the nucleus and some behaviors that are observed. Another aspect of radiochemistry that should be understood is the chemical properties of radioelements. Those elements that are only found as radioactive isotopes. They include the actinides, which are filling 5f electrons, and then technetium and promethium, which are elements that are normally found in the stable region, those elements below 83 protons, but are in fact radioactive. The students should also be able to comprehend and evaluate nuclear reactions and how isotopes are produced. This can be obtained and understood from using the chart of the nuclides. One can evaluate certain reactions. So for instance, here's a reaction shown here of a proton and nitrogen 15 makes oxygen 16. There's an alpha particle decay that makes carbon 12. That's in an excited state. It gives off a photon. Now it makes a ground state, carbon 12. The course will describe not only understanding how the particles and the isotopes react together, but the probabilities of those reactions. And that'll include cross-section data, understand what are some of the reaction particles. So for instance, an alpha particle, how that can be a product or can also be involved in a reaction. And then energies in the reactions. Where do these energies come from? Well, a lot of it comes from conversion of the mass from the starting compounds to the product. And we should also explore and understand the different types of radioactive decay. And by evaluating the chart of the nuclides, understand the location of the isotopes and what's the probability of a certain decay coming from those isotopes. For instance, heavier isotopes tend to decay by alpha. Those isotopes that are proton rich tend to decay by positron or electron capture. Those that are neutron rich tend to decay by beta minus. And then we'll discuss relationships between half-life and decays. The course will also describe how radiochemistry can be used in research, how, as an example, concentrations, very minute concentrations, down to femtomolar per liter or even less, of isotopes can be measured. My thesis work, I studied one atom at a time chemistry, so one can do incredibly small concentrations. And how we'll describe how these concentrations can be evaluated and how isotopes, making radioactive isotopes of normally stable isotopes, can be used to expand our understanding of systems. And finally, the course will investigate modern topics in nuclear and radiochemistry. This will be brought in the lectures, in discussions, and then in the final we'll have presentations, papers, and employment opportunities, which will hopefully link together what was learned in the course where radiochemistry is going today.
The course grading information is provided here.
There is a short quiz at the end of each lecture. This is broadly based upon the information provided in the lecture and is worth 17 total points in the course. There are 3 comprehensive celebrations of learning, each one worth 20% of the course grade. These celebrations of learning are broadly based on the topics for each celebration. However, previous lectures will be included. These celebrations of learning are take-homes, and the due dates are provided on the Canvas syllabus. Generally, you'll have 5 days to complete the celebration of learning, after which all the answers will be posted. And then there will be around 3 days in which modifications to the exam can be made. Any modification is only worth 50% of the grade. The goal of the celebration of learning is really to demonstrate material understanding and comprehension. And during the course, meetings can be held to discuss the celebration of learning prior to its first due date. The final exam, worth 20% of the grade, is composed of a final paper review, a presentation review, which is a video that'll be online, which I'll ask you to review and make comments on, a review of positions that are radiochemistry based, and a few questions on some overarching themes within radiochemistry. And finally, the remainder of the course points to bring it up to 100% are scored through class participation. And this is judged from discussions, meetings, office hours, Canvas interactions, and other interactions that you'll have throughout the course. The course topics are shown here, where we'll cover nuclear data, nuclear properties, decay kinetics, the different types of radioactive decay, nuclear structure models and reactions, interaction of radiation with matter, and associated dosimetry. And then we'll move on to the chemistry of radioelements. Well, the first chemistry lecture will discuss understanding chemical forms, speciation. Then we will go over the early actinides. We'll have one topical lecture on radiopharmaceuticals and radiochemistry. Then 2 lectures from the topics listed here will be selected based upon feedback from those involved in the course. The outline for the course is presented here with the topic, the date that it's online, the date that it's due, and the number of presentations for the given topic. The due date doesn't change. However, the date that the lectures are presented may change. The lectures may be presented earlier. If they're presented earlier, the due date won't change. You'll have more time to do the work. The exam dates are also listed here. As you see, we have the date online, the initial due date, and the second due date. For the exam periods, we will have, during this time between the date in which is posted and the due date, we will have office hours in which questions on the exams will be discussed. The final exam will be posted on the first day of the final exam week and will be due on the last day of the final exam week. This concludes the course overview and structure. When you've completed this lecture, please continue on to the Lecture 1 material, which covers nuclear data and information that will be used for the rest of this quarter.